In this video, we're going to take a look at how to construct and interpret an interval estimate of a population mean for sigma known. Now, let's suppose that you have a population parameter that is unknown to you and you would like to report an estimate for it. Then there are two ways that we can carry this out. The first way is we can make use of point estimates. So let's say we have a statement that reports the mean waiting time at a checkpoint is 3 minutes. Then what we're doing is we are estimating that the mean waiting time is 3 minutes. So this tells us that on average, you're going to wait at a checkpoint for 3 minutes. So that is not necessarily the exact value, but it's an approximation of the parameter that you don't have. So in chapter 7, we took a look at X bar, which is a point estimator for the population mean mu, as well as P bar, which is a point estimator of the population proportion P. We can also take a look at interval estimates, which is the second method that we're going to look at. So let's say we report that we are 95% confident that the mean waiting time at a checkpoint is between 2 and 5 minutes. So in this case, what we have done is that we have reported that we have an interval between 2 and 5 minutes where you are going to observe your mean with a probability of 95% or with a chance of 95%. So this tells you that you have a range of possible values where you have a probability of 0.95 of finding the mean waiting time in that interval. So that is what we refer to as an interval estimate. You can see that we have a lower boundary and an upper boundary for our interval, as well as a probability of finding the parameter of interest in that interval. So our interval estimate is constructed as your point estimate, which is a single calculation or a single value reported, plus or minus a margin of error. So in this case, if we want to construct an interval estimate for the mean, then you can see that our population mean mu, the interval will be X bar, which is the sample mean, plus or minus the margin of error. And if we're interested in the population proportion P, then it will be P bar, which is the sample proportion, plus or minus a margin of error. So if we report that we have a 95% confidence interval for our unknown parameter, then this means that 95% of the intervals constructed from your samples are going to contain this unknown parameter. So to begin with, our interval will take on the form of X bar, which is our point estimator, plus or minus a margin of error. Now, there are two cases that we are going to consider, and the first case will be covered in this video. So in the first case, sigma is known, sigma being the population standard deviation. So our formula is going to be X bar plus or minus Z alpha over 2, where Z is a percentile from the standard normal distribution, and we can also refer to it as a critical value, multiplied by sigma x bar, and sigma x bar is the standard deviation of x bar. So from chapter 7, we saw that sigma x bar is sigma over the square root of n, and n is our sample size. Let's take a look at the components of the confidence interval. So we have x bar, which is the point estimator, Z alpha over 2 times sigma over root n, which is the margin of error. Sigma over root n is the standard error of x bar, and this is just the same as the standard deviation of x bar. So if we graphically represent this, then we have the area in between these two solid lines, which is going to be called the confidence coefficient, and the regions outside the confidence coefficient collectively are referred to as the level of significance. So because of the property of symmetry, each of these tails is going to have a proportion of alpha over 2. Now, Z alpha over 2 is the percentile at the lower boundary here. And because of reflection, we change the sign and we get the positive value at the top here. So please take note that you need to be able to differentiate the margin of error, the standard error, and the sampling error. So the sampling error, keep in mind, will be the absolute difference between your point estimator and your population parameter. So in this case for us, it would be the absolute difference between X bar and mu. So we have 3 common confidence levels that are used, but you should be able to construct a confidence interval regardless of the confidence level given to you. So the 3 cases that we usually use commonly are the 90%, the 95%, and the 99%. So for every confidence level, we have alpha, which is the level of significance, and this is just 1 minus the confidence coefficient. So in this case, if we look at the 90%, then 0.1 is obtained as 1 minus 0.9, and that would be the same for the 95%, which would be 1 minus 0.95, and 99%, which would be 1 minus 0.99. Then the area on either tail outside of the confidence coefficient is alpha over 2. So this would be alpha divided by 2. Then Z alpha over 2 is the critical value that we'll use to obtain the margin of error. So for the 90%, your critical value is 1.645, 95% is 1.96, 99% is 2.576. So that means that your margin of error will be your critical value multiplied by your standard error. So for the 90% confidence level, it will be 1.645 times sigma x bar. 95% it will be 1.96 times sigma x bar, and 99% it will be 2.576 times sigma x bar. So we're able to get these Z values from our tables, and we can take a look at how to get the 90% and the 95% confidence level Z values. So for the 90%, we're going to look for 0.05, the probability 0.05 in our Z tables, and we find that 0.05 is between 0.0505 and 0.0495. So that means our Z value will be minus 1.645 because 0.05 is right in the middle of these two probabilities here. So that means the second decimal place will also be right in the middle of 0.04 and 0.05. So that gives you 0.045. Now, if we are interested in the Z alpha over 2 value for the 95% confidence level, we're going to look for 0.025 from the table. So we find it seated in an exact position, and the row is minus 1.9 and the column is 0.06. So our Z value will be 1.96. So if we have a 95% confidence interval, then we can state this as the probability that our mean, mu, which is unknown to us, is between x bar minus 1.96 times sigma over root n and x bar plus 1.96 times sigma over root n is equal to 0.95. So x bar minus 1.96 times sigma over root n is the lower boundary of the range of values that contain mu, and x bar plus 1.96 times sigma over root n is the upper boundary of the range of values that contains mu. So 1.96 times sigma over root n is the margin of error. 0.95 in this case will be the confidence coefficient because we have a 95% confidence interval. And 0.05 is our level of significance. So on the graph, we can see that 0.95 is the middle 95%, and on either tail we have 0.025, which will be our level of significance divided by 2. So now we can see that Z alpha over 2 in this case will be the Z value that gives us an area to the left of it of 0.025. So if we go to our tables, we'll find that Z value is minus 1.96, which is the same value here for our lower boundary. And if we take a look at the upper Z value, then we'll see that this Z value, the area to the left of it is 0.95 plus 0.025. So that is 0.975. So from the table, that Z value is 1.96. Also, because of the property of reflection, you can see that the lower value is a reflection of the upper value. Consider a sample of 16 test marks. Assume the test marks are normally distributed with a population standard deviation sigma equal to 10, and let x bar be the sample average test mark. Let this be equal to 58. So now let's calculate a 95% confidence interval for mu. So the first thing to note is what you've been given in the question. So 16 is n. Sigma is equal to 10, so sigma is known in this case, and x bar is equal to 58. So if we're constructing a 95% confidence interval, then our confidence coefficient is 0.95, and our level of significance is 1 minus 0.95, which is 0.05. So this is our interval estimate, x bar plus or minus z alpha over 2 sigma over root n. And this will be equal to 58, which is the value of x bar, plus or minus 1.96, which is our z value, since alpha over 2 in this case is going to be 0.05 divided by 2, which is 0.025. So if we look for the z value, such that the area to the left of it is 0.025, then we'll find it's going to give us 1.96. Multiplied by 10 over the square root of 16. 10 is sigma, 16 is n. So this is equal to 58 plus or minus 4.9. So that tells us that the lower boundary will be 58 minus 4.9. And the upper boundary will be 58 plus 4.9. And in this case, 4.9 is our margin of error. So our final interval will be from 53.1 to 62.9. So now we can report that we are 95% confident that the population mean mu lies between 53.1 and 62.9. Alternatively, we can also say the probability that mu is between 53.1 and 62.9 is 0.95. So from the previous example, we saw that the margin of error was 4.9, and this tells us that the sampling error, which is obtained as the absolute difference between x bar and mu, will be at most equal to the margin of error. So in this case, it will be at most 4.9. So 95% of the time, the sampling error will be 4.9 or less. And it can also be stated as the probability that the sample mean will provide a sampling error of 4.9 or less will be equal to 0.95. And this takes us back to slide 7 where we had the probability statement. Let's calculate a 99% confidence interval for mu. So we still find that n is equal to 16, sigma is equal to 10, and x bar is equal to 58. So our first step is to find our level of significance alpha. So this will be equal to 1 minus 0.99, and this gives us 0.01. So that means alpha over 2 will be 0.005. So we find that at a 99% confidence level, our Z value is going to be 2.576. And on the graph, we can see that the area shaded is equal to our confidence coefficient of 0.99, and the unshaded areas on either tail are equal in proportion. So that will be equivalent to alpha over 2, which is 0.005 on the lower tail and the same on the upper tail. So this tells us that the Z value at the top will be 2.576 and the Z value at the bottom will be minus 2.576. So our interval is x bar plus or minus Z alpha over 2 times sigma over root n. So we're going to replace our values in the formula, and this is equal to 58 plus or minus 2.576 times 10 over the square root of 16. That gives us a margin of error of 6.44, and our interval will be 58 minus 6.44 as the lower value, and the upper value will be 58 plus 6.44. So our final interval will be from 51.56 to 64.44. So we are 99% confident that the population mean is between 51.56 and 64.44, or you can report it as the probability that the population mean mu is between 51.56 and 64.44 is 0.99. So we found that the margin of error was equal to 6.44. So this tells us that this would be the maximum estimation error that we observe at a 99% confidence level. So our sampling error, which is the absolute difference between x bar and mu, will also be at most equal to the margin of error. So 99% of the time, the sampling error will be 6.44 or less. And this is the same as saying the probability that the sample mean x bar will provide a sampling error of 6.44 or less will be equal to 0.99. So if we compare the two confidence intervals that we've just constructed, we can see that for the 95% confidence interval, the width, which is the upper value of the interval minus the lower value, gives us a width of 9.8, and the width for the 99% is 12.88. So we can see that when we increased our confidence level, we also ended up increasing the margin of error, which ultimately increases your interval, and that's why you have a larger width. So if you want to increase your chances of finding mu in an interval, then that means that your interval is going to lose the accuracy of estimating mu. So if you want to be more accurate when you estimate mu, then your confidence level has to be decreased. So in terms of interpreting our intervals, then for any confidence interval, we can state that we are 1 minus alpha percent confident that the population mean is between the lower limit and the upper limit of the interval that we've constructed, or there's a probability of 1 minus alpha that the sample mean x bar will provide a sampling error of z alpha over 2 sigma x bar or less, where z alpha over 2 sigma x bar is the margin of error. So the interpretation depends with the question or the scenario that has been given to you. So now we know that our confidence interval for any level will be x bar plus or minus a margin of error, and our margin of error is a z value times our standard error, which is sigma over the square root of n. So this means we can make use of our Excel functions, and this will be, our margin of error will be equal norm.s.inf, and in the brackets it will be alpha over 2, and this gives us our z value multiplied by sigma over the square root of n. There's also a shortcut formula, and this is the confidence.norm formula. And in the formula, we're going to place alpha, our level of significance, comma sigma, the standard deviation from the population, comma n, which is your sample size. And in this case, we are placing alpha since it's going to return to us a margin of error for a two-sided confidence interval. Now, in the next video, we're going to take a look at how to construct and interpret an interval estimate of a population mean for sigma unknown. We're going to take a look at the t-distribution and how to use it to construct an interval estimate for a population mean. And we're also going to look at how to do interval estimation for the population mean with the help of Excel.